Assertions, sometimes known as anchors, are little tests embedded in regular expressions to ensure certain conditions exist for a match to occur. This video will focus on these assertions as they are an important concept and most practical usages of regular expressions revolve around assertion. Just taking a moment to clarify that like Flag's discussion in previous video of our regular expression playlist, understanding assertions would unlock the processes parsing engines use to make regular expressions work. That is why I kept those concepts in the start when your mind is fresh. In later videos, there would be a cascade of terminology to exhaust your brain. But many of those terms keep repeating in all regular expressions you come across, so you eventually absorb them anyway. With this little background, let's go over its formal definition. So formally, assertions are constructs to test whether input string meets a certain condition at specified position, but not consume characters. Reading this formal definition makes you realize that this is not human comprehensible by any means without examples. So let's break it down and then go over some assertions with examples, and then it would start to make sense. First, let's focus on the defining characteristics of assertions, that is, they don't consume characters. So, what is consuming characters? By consuming characters, we mean that regular expressions take an input character from input string, test if it matches regular expression or not, and then pick the next character and continue. Assertions, on the other hand, test the next character or characters for a match, but once that evaluation is done, the first character is used to check for next match with the non-assertion portion of regular expressions. There's a slight difference if you followed. We'll discuss this behavior in Lookahead and Lookbehind assertions where it would make most sense. But for now, let's focus on input boundary assertions. We discussed them in detail in our flags video when evaluating the M flag, but let's go over it again. These are the cap and dollar characters that assert that current position is start or end of input string respectively. If M flag is set, they assert start or end of a line. They are assertions, so they don't consume any characters. First, let's understand what cap and dollar mean. Cap is a beginning of line assertion, so a regular expression like cap the would match the quick brown fox, but not James the fox, even though both have the word the in it. It only matched input where the word the appeared in the start. Please recall from our definition that assertions are little tests embedded in regular expressions to ensure certain conditions exist for a match to occur. This is what is happening here. Dollar is the opposite of cap and it is the end of line assertion. A regular expression like fox dollar would match both input strings earlier since both end in the word fox. So I do have a bias towards JavaScript as this video series is made in context of full stack course on this channel, but let me introduce some related anchors that are not found in JavaScript, but in many other useful languages like .NET, PHP, etc. So you might come across some other anchors like backslash a, backslash z, and backslash small z. Backslash a matches the start of a string and is same as cap, except it ignores the multi-line flag, so it can only match the start of first line in a multi-line string. Note that backslash a is not supported in JavaScript, but for other languages, it is a great convenience with unambiguous meaning as you don't have to remember about multi-line flags and all. Backslash z and backslash small z work similar to dollar without multi-line flag, with a slight difference. Both only match end of string, so last string of multi-line with a slight difference. Backslash z, that is the capital Z, would match end of line even if the string terminates with a new line character. That is, it would ignore the end of line character at the very end of the string, while backslash small z would only match strict end of line. So if we have two lines, first and last, on two separate lines, in fact, let's go to Regex 101 and see this in action. And let's come up with a very simple regular expression with just the word t to match and followed by backslash c. No flag set, PHP being selected, not JavaScript. Okay, now note that this last T of the last line is being matched with backslash capital Z and also small z and also dollar sign without the backslash. Okay, let's go back. Right, let me show you the difference between capital Z and small z. So if I press an enter, which is the case with some languages where they read input from a file line by line and add a new line character at the end. So backslash small z is not matching the T if the new line character is present, but backslash z is gonna match. So this is the slight difference that you need to be aware of. Note that no multi-line flag is being set and it would have no impact on these characters either. Let me quickly show you the example for cap and backslash a as well. So I can say my first and my last, and now it should match. So the cap without multi-line flag is only selecting the first characters of the first line. With multi-line flag, they are going to select both of these. But if I replace cap with backslash a, then only the first word of the first line is going to be selected, and it is not going to be affected by multi-line flag. That's the behavior you are stuck with. Right, now for more interesting assertions. A look-ahead assertion looks ahead to check if subsequent input matches subpattern given in look-ahead assertion, but it does not consume the input while looking ahead. If match is successful, the current position in input remains the same. Let's follow the syntax. The syntax for such assertions is in parentheses question mark equal to the subpattern. Right? There's an alternate way available as well in which you provide parentheses question and a negative subpattern. So the first look ahead assertion matches if the input matches the subpattern, and the second assertion matches if the subpattern does not match the input. A bit counterintuitive, but sometimes you do want a not assertion. So that is why the syntax is provided. 99% time you are going to stick with this one. Let's focus on this one first. For assertion to succeed, the pattern must match the text after the current position. But current position remains the same after assertion is done. Let's go over an example to understand. I found an excellent one on MDN website which explains concept in details, but it is a head spinner, so feel free to skip if you are seeing flying stars or head spinning. Do note that the slides for look ahead assertion would clarify regular expressions like no other if you are able to digest them. So I would strongly suggest to pay attention and try hard to understand even with repeated attempts. I shall explain two fundamental concepts of regular expression before moving on to the example itself. To explain the example, I have to look ahead and explain a concept called captured groups to you, which will come later in regular expression video series, but short version is if you enclose a part of regex in parentheses, you can refer to the match substring it captured using \1 \2 later in the regular expression itself. As an example, consider regular expression parentheses AA XYZ \1 and input string AAXYZAA. Now capture group would attempt to match AA with input string and find a match right at index 0, that is AA. Now it would store the match result as value for first capture group, now accessible via \1. Captured groups are numbered in order of appearance, so first capture group in regular expression can be accessed later as \1, second as \2, etc. So now the regular expression matches as normal until it reaches this part. Now it must evaluate what \1 means. So it would look at the result of capture group 1 evaluation and find the result AA. It would replace the \1 with AA and go ahead with the match attempt. The part of input string following XYZ is also AA, so it's an exact match. The entire input string is a match for our regular expression like this. Yay! Right, the next concept which is absolutely critical to understanding how regular expression work is backtracking. Please do watch attentively as this is one of the most important concepts of regular expressions. Backtracking occurs when a regular expression contains optional quantifiers or alternative constructs, which are formal term for our clean stars, clean plus, dot star, etc., and alternatives using pipe symbols, for example, A pipe B, respectively. To make contrast clear, if your regular expression does not contain any optional quantifiers or alternatives and is a plain match like ABC and an input string say ABCD, then the parser would perform a linear comparison attempt. That is, take first language element in regular expression, match against the input string, then the next language element or group of elements in input string, and so on, all the way until match either succeeds or fails. If, however, an optional quantifier like A star, A plus, dot star or an alternative like AB, pipe C does exist, then things work differently. Using something called Neo Deterministic Finite Automation or NFA engine. You don't need to remember that. Take an example of regular expression dot static EF and input string A, B, C, D, E, F, G. The parser would start with dot static and see how many characters it can match. And it goes A, B, C, D, E, F, G and sees the end of input string. At this point, it would try to match EF part of regular expression with the next characters in input string, which, well, don't exist. So the match was unsuccessful. The parser in this case, based on its default settings, tried to fully match optional sub-expression in regular expression, that is the dot static part in first attempt. However, if the match was unsuccessful, it is ready and willing to give up a portion of successful match of sub-expression and return to earlier saved state in interest of matching regular expression as a whole. The top priority is matching the entire regular expression. This process of returning to a saved state to find a match for entire regular expression is called backtracking. Let me explain. So in our example, the parser would start giving up the matched value of dot static one by one, which currently is ABCDEFG, one character at a time, as it saved a state during capture of each character. So it first gives up G and attempts to match. So ABCDEF, and then it tries to match EF, which again fails because of the extra F present. The parser now backtracks again and also gives up F. So now it is left only with, so the dot static portion is only left with A, B, C, D, E as its captured row. But it is still A, B, C, D, E, E, F, so match is still unsuccessful. Next time it is gonna give up that E as well and then left with A, B, C, D. And now we try to match the string A, B, C, D in place of dot static followed by E, F and it's an exact match. The end goal is achieved. The regular expression finally matched. Win for the backtracking, a sacrifice for greater good paid off. Backtracking, as you just saw, has a performance cost, and this cost can significantly rise if you're not careful with optional constructs. Here we just backtracked twice or thrice, but if you're using optional constructs in nested way or in alternatives or with a large input string, it can really hit back. If used properly, backtracking is what makes regular expressions so flexible and powerful. They are the true force behind regular expressions magic. Alright, now I must introduce an exception to the norm of backtracking. Backtracking does not work with atomic groups, which include captured groups. If a parser starts evaluating a regular expression and is done evaluating an atomic or say captured group, then the value is final and would not give a portion of its captured value. Or should I say, it won't backtrack even if regular expression fails. If you're using back references like \1, \2 to refer to these values, then values remain fixed and do not take part in backtracking. Now that you're aware of these concepts, we can head back to Lookahead assertion example and put them both to use. I'll start with a simpler example first before going to the more complex example to make transition for you easy. If you want to skip this example, please feel free to do so. So regular expression, parenthesis, question equal to a plus, and then ab, and then \1 as a back reference, along with the input string aa, baa. Alright, let's see how it works. So the lookahead assertion being used here with sub-expression a plus is an atomic group now. So A plus would look at the input string and greedily match AA. AA is now the result value of this captured group and can be back referenced using \1 later in the regular expression. Okay, we are now done with the look ahead assertion, and the parser is now going to try and match the regular portion of regular expression, that is the AB part, with input string, and immediately fail as it finds AA at start of input string, which does not match AB. Match attempt at index 0 is unsuccessful. Before going ahead, note this as this is important. When assertion matched A plus with AA, it did not move the current index ahead. So after assertion was evaluated, the regular expression started to evaluate the next part of regular expression from start of input string, not from index 2, that is BAA part. Assertion did not consume characters from input string. Hope that that thing is solidly clear by now. All right, let's resume our parsing example. So since the first attempt from index 0 was unsuccessful, the parser starts afresh from index 1 of the input string. The assertion sub-expression A plus is now this time evaluated to A only. And remember, A plus means one or more repetitions of A. So 1 is perfectly fine. So A value is assigned to this atomic captured group. After the assertion, the AB part of regular expression does match with input string at index 1 as AB equal to AB. Then parser finds \1 in regular expression and replaces this with the value of captured group 1, which is A. The next character in input string following AB is also A, and hence the match is successful. The regular expression completely matched the string ABA of the input string. Right. To make it even more clear, let's go to our consumption example and hopefully it will make sense in this one. So let's begin evaluating this regex with an input string. So the parser would start from the left while the current index in input string is at 0 and find a Lookahead assertion here, which would fail for B as A plus requires at least one or more A symbols to work. So it would go to next character at index 1, which is A, and restart. The look ahead which now match, and since it looked ahead and greedily looked ahead, it would find this A character which is also a match. So the look ahead assertion passed and the value of this captured group turned out to be AA, this one. Alright, our look ahead assertion evaluation is now complete. The parser now starts to evaluate the regular expression or the regular part of regular expression, which is A static B. And remember, we were at index 1, which is the second character. So if you recall, A static means 0 or more repetitions of A. So A static B matches this part because AA matches the A static and then it is followed by B. So that part is evaluated correctly and matches. Next, the parser finds \1, which is a back reference to the first captured group. And if you recall, since we started afresh from index 1, the value captured by this captured group was AA. So \1 is replaced with AA and the parser continues. So the parser tries to match AA with AC now and fails because the second letter does not match. A does not match C. Now the parser would attempt to backtrack, but if you recall, we mentioned that the atomic groups, which include the captured groups, do not backtrack. So the value captured by this captured group, that is AA, is final and it cannot be backtracked into A or something. So nothing can be done at this stage and the match attempt at index 1 is a failure. Now the parser would move to index 2 and try to evaluate. Remember the most important point, the evaluation starts afresh at index 2 for the entire regular expression including look ahead. So the look ahead assertion and captured group value would be re-evaluated. So now the A plus at this stage is going to evaluate only to A, and after that The asterisk B portion is going to start from the current index, which is the value 2, and it is also going to find A and B, which is a match for asterisk B, because one repetition is totally fine, and then it finds B, so this portion matches exactly. Now we come to this backslash 1 part, and if you recall, the A plus had evaluated to a single A this time. Backslash 1 is replaced by A with the parser and a match attempt is made. This time it is successful because the A following the B is a match for backslash 1 this time. I provided all the steps in this huge text-ridden slide. You can pause and try run this example multiple times if anything was confusing. I hope you understood how this worked, as it gives the best intuition into how the regex matching actually works behind the scene. If you understand this properly, working with regular expression would be really easy. This slide and the backtracking slide should really help going forward. Okay, what we just looked at was positive look-ahead assertion. A quick parting note on the negative look-ahead assertion, that is the one with exclamation sign, that it is just the opposite of look-ahead regular assertion, where assertion would pass if pattern does not match. I'm not going in detail as it is pretty straightforward. It is also useful in some cases. We are running out of time, so let's see some other concepts. The greedy behavior of quantifier can be controlled in regular expressions. There also exist lazy and possessive flavors that can plug or enhance the greedy nature of certain matchers. This is not a topic for this video and would be covered in detail with quantifiers in this series. Just showing you that if you add a question mark symbol to a quantifier, it becomes lazy and does not want to match anything until forced to. Exactly the opposite of greedy default. The possessive flavor, which is supported in limited languages, is a greedy plus version and is activated by adding a plus suffix to quantifier. And it would not only be greedy, but would not give up its captured value during backtracking. A great example is dot static question, where dot static would greedily match any input string, but putting a question mark makes it non-greedy, so it would match nothing by default and only work with backtracking. Let me show you in test website. Alright, so let me first type a regular expression dot static and a bbc, and it is matching everything, right? But if I introduce a question mark here, it matches nothing, right? And it says static question matches the previous token between 0 and unlimited times as few times as possible, expanding as needed, right? So it would expand if needed. So if, let's say, I introduce DDD here, then it is forced to match in order to match the entire regular expression for the greater good. So that's when the question mark would go on matching anything in the input string forcibly. Okay, let's have a quick look at the plus sign as well. So if I go here, in fact, dot static is a paired example for this. So I say a static plus, and it's gonna capture all the A's, and here it also says it matches the previous token between 0 and unlimited times as many times as possible without giving back. So now if I type AB at the end, then it could have given up one A in order to match this part with this, right? Uh, Giving up one A out of 4 to be left with 3, but it didn't, right? If I remove this, then you see it matches the entire string. If I introduce this, it would also match because it is giving up one A in backtracking to match the entire expression, but plus won't do so. Plus is gonna capture a value and it's gonna stick with it. Okay, our final topic for this video is look behind assertions, with the syntax being in parentheses question mark left arrow equal to subpattern for positive look behind assertions, and parentheses question mark left arrow exclamation mark subpattern for negative look behind assertions. So look behind is similar to look ahead, but with a difference that it works on the opposite side and after the matcher has done its job on the expression to its right. So unlike look ahead, which greedily captured maximum characters from input string that matched its pattern, look behind works on leftovers, grabbing what is left after the pattern to its right has made a match. Whatever is left over is consumed by look behind. That would be clear with examples. So as an example, consider this, right? With the input string zyx. So this expression would match only because the parser is going to start matching x first. So it would go matching z and fails, y with x and fails, and then it finds a match with x at this point, right? And after that, it is going to start evaluating the look behind assertion. It has taken note that a look behind assertion exists, but it hasn't evaluated it yet. It evaluates after the match has been found to validate that the assertion holds. So now it is going to check whether there is a y on the left side of this x, and it is going to find one. Right? I hope this is clear. So with example two, we have a situation where we have an input string grab a $2 coffee, and we are trying to find prices in a phrase, right, without the dollar sign. So what are we going to do? We are going to have this regular expression where the look behind assertion is that there exists a dollar sign, and you know that dollar is also an input boundary assertion. So what we are going to do is we are going to tell the parser that this is not the same dollar. It is, we are trying to use it literally, right? So we are going to add a backslash to it, which is going to instruct the parser, don't treat it as the input boundary assertion, treat it as a dollar sign character, right? And then followed that is the normal part, and this backslash d is the opposite kind, where d is just a regular character, but backslash d indicates to parser that we are trying to match a number, right? It's for digit or decimal. So backslash d plus is going to capture any number string. So it could be 22, 2002, and it's just like a quantifier, a digit based quantifier. It's going to grab all the numbers that come forward. So it's going to match all numbers. Following that is backslash dot, and if you, I think you understood by now that backslash changes the meaning of the character. So if it's a special character, it makes it a normal character. If it's a normal character, it gives it a special meaning if applicable. So dot has a special meaning. It's a wildcard, so we use backslash dot to just treat it as a regular character, followed by a question because dot is optional. It could be 2.5 or $2.7 coffee. So for that situation, we say optional dot followed by an optional number, right? So since it doesn't have zero point 0.5 or something, that is completely okay. So this example is going to match just the two part in this phrase. I'll take a minute or two to explain this backward processing I talked about for the look behind assertions. So I don't think that made sense without an example, so here we go. So consider this regex where we have a look behind assertion, as you can see with the backward arrow, and I have this sub pattern defined in here with two capturing groups created inside. So and we are using the input string ABC. So the first capturing group is gonna check if the input string is has A or AB appearing, and the second capturing group is gonna check for presence of BC or C. And both of these can occur one or more times. So they are gonna capture at least one character of each of the constituents. So if we were talking about a regular expression, then of course what should happen is that the first capturing group, A or AB, should capture AB because that is evaluated first. And then leftover is C for the second capturing group. But since our look behind assertions are processed backwards, they not only are processed after the regular expression afterwards has evaluated, they also get processed from right to left, then the opposite is going to happen. So let's go to Regex 101 and have a quick look, which is our test website for regular expressions. So I've already written our regular expression right here, and I'm going to write a, B, C here. Right, and let's evaluate what happens here. But first, let me show you what the group names are. So the first capturing group is the outside one. So if you remember, the capturing groups are given a number from the opening parenthesis from left to right, and that stays true even if we are in look behind assertion, look ahead assertion. That rule does not change. The capturing group number is assigned from the first opening parenthesis from the left. That holds true even for nested capturing groups like these ones. So the first capturing group is the outside one, the entire thing. The second capturing group is this one, A or AB, and the third capturing group is this one, B, C, or C. Ideally, in a regular expression, a normal regular expression, A or AB would match AB, and the third capturing group is gonna be left with C. But what happens here? The group 1 evaluates to the entire regular expression. That's fine. The group 2 evaluates only to A, not AB. And the group 3, which is this one, captured this BC part. And the reason, as we explained earlier, is because the expression was evaluated right to left, not left to right like a normal expression. So if I remove this backward part, then this should change. And see, if a normal in a normal scenario, AB is going to be captured by group 2 and C, which did not happen. The opposite happens with look behind assertions. Right, that covers the look behind assertions. Let's go to our next one, which is the word boundary assertion. That's the last one. So the syntax is backslash small b and backslash big B, and you need to be careful with those because backslash b small b returns true if word boundary is detected, and the backslash capital B is opposite of backslash small b. That is true if not a word boundary. And what is a word in regular expression terms? Word is an alphanumeric characters and optionally underscore. So A to Z capital, A to Z small, 0 to 9 and underscore, they all constitute a word. And a shortcut in regular expression syntax for that thing is backslash W, which means a word character. So you can use it anywhere in your regular expression, just like backslash D that we used in an earlier example. So that is gonna capture a word. So let's head over to regex 101 again and try out an example. So let's get rid of this, and I'm going to say hello world, and I'm going to say backslash B here. So it found one match right over here. And if I open the global flag, and remember we are getting 4 matches because this is a word boundary assertion. It matches any place where a word is starting or ending. So it is capturing all start and end of a word. So if I remove this and just leave ABC here, then it's gonna have 2 matches at the word boundary, right? I hope that makes sense. You can make it even more specific. So if I say A and then we have D, E, F here, then it's only going to capture the word boundaries which are starting with the letter A, right? Not any other word boundaries. So that is how you can make it more specific. Similarly, C slash B is also going to work. It is going to detect a word boundary here, but B/B is not going to work. It's not going to match anything because B appears in the middle and does not match any word. All right, finally, let's quickly try \B, and it is going to detect anything which is not at a word boundary. So it captured everything in the middle, which are not at the word boundary. Nothing at start, end, or between spaces. Right, I hope this is clear. And that brings us to the end of the regular expression assertions video. I hope you were able to get a feel of how regular expressions work and how these assertions work. This video was meant to give you a deep intuition into how regular expressions match the strings and the inner workings of the parser, which I hope you are able to understand. So now in the series we are going to continue on other aspects of regular expression. So don't forget to watch. If please give a thumbs up if you like this one and subscribe to be notified of the upcoming content. Thank you so much for watching.